Good afternoon, and welcome to our group project presentation. On behalf of my group, consisting of James Cho, Jeremy Hakian, Jacob Sultan, Derek Wiggum, and Kosuke Fujiwara. My name is Jeremy Rafter, and I'm going to be telling you more about assessing on-road freight emissions for Patagonia and evaluating low-carbon fuel alternatives. So the client for our project, as Fru just told you, is Patagonia, and they're an outdoor apparel retailer located in Ventura, California, and they're a medium-sized company. And probably Patagonia's most defining characteristic is their strong environmental reputation. So that's pretty evident from looking at their mission statement, which says to make the best product, cause no unnecessary harm, and use business to inspire and implement solutions to the environmental crisis. So since Patagonia has this strong reputation, sometimes they have to defend this reputation. And that's exactly what happened a little over a year ago, before we started our project. Patagonia received pressure from an environmental NGO to avoid the use of diesel produced from tar sands in the distribution of their products. And if you're wondering what tar sands are, here's a picture. So it's an alternative way to produce diesel. It's another source of petroleum. But instead of pumping it out of the ground, it's found in the surface of the earth in this form. And to get the usable petroleum out of this product is extremely energy intensive. It has to be heated up to very high temperatures. And it's generally considered to be an environmentally unfriendly process. So not owning any of their own distribution vehicles, Patagonia had limited knowledge about the extent to which tar sands was used in their distribution network and what the associated impacts were. So they enlisted our help to quantitatively evaluate their distribution network. And more specifically, we sought to answer the following questions. So we wanted to know what the current baseline emissions associated with Patagonia's distribution network were. We wanted to create a tool that profiled alternative fuels and their emissions. And lastly, and most importantly, we wanted to develop actionable recommendations for Patagonia to reduce their emissions and respond to this pressure. So we know this project is significant to Patagonia because they face these NGO pressures, but what's the broader significance? Why should you care about this project? So freight emissions in general are a major source of emissions, and as you can see from the graph on the left, freight emissions have been steadily increasing since 1990. And the light orange in these graphs represents freight emissions specifically from trucking. And that's also represented in the pie chart. So as you can see, a large majority of freight emissions come from trucking, 74%. So not only can Patagonia improve their reputation, but they can also serve as an example of a way a company can address this large problem. So that's the broader significance of our project. So an important first step as we started our project was defining a very clear scope. So we only looked at domestic shipping, excluding Hawaii, and of those shipments, only those done by Class 8 heavy-duty trucks. The time period we considered was the 2012 fiscal year, and we only looked at currently available fuel types. When evaluating these fuel types, we looked at the complete fuel cycle emissions, and we looked at one impact category, global warming potential, because that's what Patagonia expressed interest in. So a few of these scoping terms need a little extra definition. First of all, a Class 8 truck is defined as a truck with a gross vehicle weight rating of 33,000 pounds or more. And this includes all tractor trailers that you would think of. The complete fuel cycle is defined as the combination of upstream and use phase emissions. So upstream emissions are those emissions associated with the production of the fuel, getting it out of the ground, refining it, and transporting it to the point of sale. And use phase emissions are those emissions associated with the consumption of the fuel. And typically for a normal diesel or gasoline vehicle, the use phase accounts for about 85% of the emissions. So I said we were going to look at all currently available fuel types, so here's the list. And first is conventional diesel, so this is what almost all trucks use currently. And then we also considered 3 types of biodiesel, including biodiesel from algae, soy, and B20, which is a 20% blend of biodiesel and 80% conventional diesel. We looked at compressed natural gas, 2 types of liquefied natural gas, including LNG produced from conventional sources and also LNG produced from landfill gas capture. We looked at propane, vehicles powered by electricity, and then also several types of liquid and gaseous hydrogen, depending on the upstream production process. So having defined the scope, we moved on to primary data collection. And our data was collected within the context of Patagonia's distribution network. So it's important to understand how this works. So Patagonia products arrive in the country to either the port of San Francisco or the port of Long Beach. And Patagonia uses the freight forwarder Expeditors International to move the products from these ports to their distribution center in Reno, Nevada. And then from there, they use UPS to distribute their goods via 3 channels to the rest of the country. So those goods either go via retail, which means they go to a Patagonia-owned retail location, direct to customer, which is what would happen if you ordered something online and it arrived at your home, or wholesale, which refers to products going to a place like an REI or an EMS. So we had to figure out a way to quantitatively represent the movement of this freight with numbers so we could assess the emissions. And in order to do that, we used the ton-kilometer freight metric, which is simply 1 metric ton shipped 1 kilometer. Or to put that in slightly more relatable terms, if you can imagine an elephant being shipped on a truck across campus, that would be about 1 ton kilometer. And in order to obtain this data, we looked at weekly freight forwarder billing statements. So with that, each shipment had a listed mass and a listed address it was shipped to. And this facilitated the calculation of these ton kilometer totals, which you see on the right. And so for the whole year, over 5.5 million ton kilometers represented the distribution of Patagonia products in the US. So you can imagine that elephant going back and forth 5.5 million times. That's kind of what happened. So now that we calculated these freight totals, we had to find a way to relate this level of freight to a level of emissions. And to do that, we built a model, and this model at its core was built around the calculation of emission factors. So to calculate these emission factors, we had 3 main parts. So the first part was greenhouse gas emissions per unit energy. So what would the emissions be from using 1 joule of diesel, for instance? And this data came from pre-existing research, and we represented it as E. We also modeled fuel consumption. So we had Z, which is the fuel consumption rate, and this is based on things such as vehicle age, driving cycle, and most importantly, package characteristics. And the third piece was Y, which is a conversion efficiency factor, and this relates different energy efficiencies of different alternative fuel technologies to each other. And then combining these 3 factors together, we were able to calculate our emission factors for each type of alternative fuel. And when talking about emission factors, it's very important to keep the units in mind. So the units of these emission factors are grams of CO2 equivalents per ton kilometer. And now James is going to tell you a little more about how we utilize these emission factors.
So with this model, we now had an essential tool to calculate the emission factors that we needed to reach our objectives of getting a baseline of Patagonia's emissions and looking at strategies. So with this, we took this model and we calculated the emission factors for each of the fuels. And they're shown here, listed along the bottom. We have all the fuels that Jeremy mentioned. And the height of each bar represents the amount of emissions released per ton kilometer of freight shipped by that fuel. And we actually calculated this emission factor in 2 segments. The orange segment represents the upstream part of the emissions. Again, that represents the production, extraction, refinement of the fuels. And you may notice that in some cases, this emission factor is negative. That's in the case of the biodiesel. For example, with the soy and algae, when it's grown, it takes up carbon dioxide from the atmosphere and thus reduces the amount in the atmosphere. So it receives a credit for that emissions reduction. Or in the case of the landfill gas shown on the right part of that circle, that represents the emissions, avoided emissions, that is captured from the landfills and instead is used for the liquefied natural gas. The blue segments represent the emissions related to the use phase of the emissions. So this is the consumption of the fuel in the vehicle itself. And what may stand out is that some of the fuels have no related use phase emissions. That's in the case of the electric and hydrogen fuel cell trucks. They have no tailpipe emissions for GHGs, and so all of their emissions are related to the production of the fuel itself. So with the upstream and the use phase emission factors, when you add them up, you get the total fuel cycle emission factor shown here. So we now had a way of comparing the emission factors for each type of fuel and the vehicles used. And what we wanted to do first is to look at the tar sands. Again, that's the initial motivation of this project, was considering the emissions from tar sands. So we calculate the emission factor for diesel in 3 ways. The bar on the left shows you the average emissions related to diesel in the US. So this is the emissions related to diesel that you get from any pump in the US on average. The other 2 bars indicate the emissions related to diesel produced from tar sands instead. And the middle bar shows you the lower end of that range of tar sands related emissions, whereas the bar on the far right shows you the high end of the range of emissions related to tar sands, because there are different production methods for diesel produced from tar sands. The tar sands, as you may see, has higher related emissions as compared to the average consumptive mix of diesel in the US. So this seemed to justify Patagonia's interest in looking at tar sands more closely. However, with some further research, we learned that from the understanding the production of fuels and distribution of fuels, that it's difficult to go to a pump and ask for tar sands for diesel. It all gets mixed in refineries and sent to all the pumps in the US, and so you can't be sure that the source of any given source of diesel in the US. This was a challenge in comparing the objective of avoiding tar sands. Our objective, though, of achieving the baseline emissions rate for Patagonia's freight, we calculated the emissions rate with the average consumptive mix of diesel and multiplied that with the total amounts of freight that Jeremy mentioned earlier. That's the 5.5 million metric ton kilometers of freight moved. By multiplying that with this emission factor, we were able to calculate the total emissions related to freight shipped for Patagonia in 2012 by Class 8 conventional diesel trucks. And that was about 534 metric tons of CO2 equivalents. We broke down that total into the 4 distribution segments that Jeremy mentioned earlier. On the far right represents emissions for the inbound segment. So that's emissions from moving the freight from the ports to the distribution center. While the other 3 bars in the middle show you the emissions related to the distribution center, to the stores and customers, and those freight emissions. So now we had an idea of what the freight-related emissions were for Patagonia in 2012. And now it's time to get to our other objective of ways to reduce these emissions. So we first considered looking at shipping this freight by alternative fuel trucks. So we looked at our emission factors for all the different types of fuels, and we first eliminated those fuels that had higher emission rates than diesel. So any fuel with a bar higher than this red line indicates that it would emit more greenhouse gases for shipping freight than by diesel. So we eliminated those choices, which left us with a little less than half of the original fuels to look at. From there, we further narrowed down the fuels to look at by looking at only those fuels for which Class 8 trucks currently exist, which left us with 3 options to consider. diesel hybrid electric trucks, trucks using B20, the biodiesel blend, and LNG trucks using landfill gas. Now that we had those three fuels to focus on, we wanted to see what would have happened to Patagonia's emissions had they shipped their freight by these alternatives instead of conventional diesel. So to do that, we created a diesel replacement scenario graph. On the left side is business as usual. What happens when freight is shipped by conventional diesel trucks? And that gets us to that 534 metric tons of CO2 that I mentioned earlier. As you move to the right of the graph, shows the increasing shipments of freight by each alternative fuel truck. So for example, if 50% of the Patagonia's freight in 2012 had been shipped by LNG trucks, which is represented with that green line, then instead of having 534 metric tons of CO2 emitted, would have had about 300 metric tons instead. Similarly, using the other alternative fuel trucks would have reduced the freight-related emissions, but more modestly than compared to LNG. So this seems to suggest that Patagonia could reduce its emissions just by switching the types of trucks that are being used. However, this was challenging because Patagonia, again, doesn't own its own shipping fleet and contracts with third parties. So we found this as a challenging recommendation initially. So we wanted to look at if there are other possibilities for reducing freight-related emissions. And so what we did is we did an investigation called a sensitivity analysis. With the sensitivity analysis, we looked at different factors or parameters that affect emissions. For example, looking at driving cycles, so whether trucks are driving on highways or urban roads, or looking at the types of trailers and the maximum payload that they can haul, or characteristics about each package, so the size and the weight of the packages. And by playing around with these numbers, we saw that the density of the packages seemed to have a big impact on the total freight emissions. So we decided to look at this strategy more carefully. So here we plotted the amount of emissions that related to the density of the packages. So the current density, average density of Patagonia packages is about 107 kilograms per cubic meter, represented with the blue line there. And what we did is we imagined what would have happened to the emissions had they increased the density by 10%. So that'd be like packing in 10% more mass into the same size packages. And that's indicated here with the orange line. And so what you can see is that there would be a reduction in emissions of about 40 metric tons, or about a 7% decrease. So we now had a new strategy to consider offering to Patagonia. And we wanted to compare how this strategy worked against the fuel switching strategies that we discussed earlier. So back to our diesel replacement scenarios. We overlaid this with the emissions reduction from increasing the package density by 10%. And what this analysis could show us is that if packages, 50% of Patagonia's packages in 2012 had been shipped instead by trucks using B20, which is that blue line there, then that would match the emissions reduction from increasing the package density. Or in the case of LNG trucks, 9% of Patagonia's packages would have had been shipped by LNG trucks using landfill gas to match the same emissions reduction as that from increasing the package density by 10%. So now we were able to compare the emissions reduction results of the different strategies. We wanted to consider other characteristics about these strategies before arriving at our final recommendations. So to compare the characteristics, we created a decision matrix. Along the left side, you see all the strategies that we looked at: increasing package density, incorporating different types of alternative trucks, and at the bottom, avoiding tar sands. And of course, these were chosen because they meet this criteria of emissions reduction, and thus they all meet the criteria to get the green check mark. However, in the criteria of uncertainty, we are pretty certain about the emissions reduction related to increasing package density and using more efficient diesel hybrid electric trucks. However, there is debate as to the emissions amounts related to these alternative fuels. Because they're such new and emergent technologies and production methods are still being developed, there's debate as to how much emissions should be assigned to each of these types of fuels. And so because there's great uncertainty with the emissions related to these fuels, they receive this X, the red X there. The final criteria is the feasibility of implementing these strategies by Patagonia. Again, package density is something within the realm of control for Patagonia. However, they have no direct control over what kind of trucks and what kind of fuels are being used, since they contract with these third parties. And so this reduces the feasibility of implementing these strategies directly. So with this information, we felt like we had enough to recommend to Patagonia the following strategies. First and foremost, we recommended increasing the density of the shipped packages. However, we still also recommend working with the shipping companies to incorporate more of these alternative fuel trucks. And we first recommend working with Expeditors International, which is a shipping company that moves their freight from the ports to the distribution center. They have a working relationship with this company and have worked with them in the past to reduce the distances traveled by the packages. So we feel this is moderately feasible. And we also recommend working with the other shipping companies that ship their goods from the distribution center to the customers and stores. And this is mostly with UPS. And although UPS is a huge logistics company, we feel that if enough companies like Patagonia insist on the use of these alternative fuel trucks, then eventually UPS will change its strategies. So with these recommendations, I want to bring us back to our closing, back to our initial motivation for this project, which was to look at the tar sands and the related emissions. Tar sands can have a big effect on the environment, especially with emissions. And this is an example of tar sands operation. We feel that as we researched that avoiding tar sands at the pump is infeasible in practical terms. You just don't know what you're getting at the pump. So instead, we offered Patagonia different strategies to reduce their emissions for shipping. And by doing so, we hope that Patagonia can stay true to its original mission statement and become a leader for other companies to follow. And by doing so, can help reduce this global issue of transportation emissions. So we'd like to take a moment to acknowledge all the people who were involved with this project in the past year. Our advisors, Roland Geyer and Brandon Kaczynski, all the people at Patagonia, Alyssa Lohman, Jill Dumaine, Deidre Williams, and Tony Ferguson, our external reviewers, Yardi Systems Group for their support, and all the people here at Bren, and of course all the friends and family who came to support us today. Thank you so much.